Ready.
Hello, my name is Josh Salinger and I'm the owner of Birdsmouth Design-Build. We are a residential design and building company here in Portland, Oregon. And standing in front of one of our projects, this is an ADU. It's a zero energy, will actually be a positive energy once we're all said and done. This building is going to create more energy than it consumes on site. And our company is really focused on mitigating climate change through the built environment. So, buildings use 39% of all the, or emit 39% of all the greenhouse gas emissions in the United States. So if we want to make the biggest impact with climate change, buildings are one of the biggest ways we can do that, more so than transportation and more so than industry. So I started this company to really make a difference in our fight against climate change. I've got 2 kids at home and I know that they are going to be dealing with climate change either directly or indirectly in their lives. And so for me to start a company and address this head on is really meaningful and I think will really affect climate change and the people that live on this planet. So really love doing it because it's also really creative. Building zero energy buildings requires input from the design team and the architects that we have on staff, along with our builders as to how to put these things together really well. And putting that all together is just a really great creative process. And it's just really exciting to be able to show everyone some of these methods and ways that we're putting these things together. So really excited to show you this project. Okay, everybody, we're here at in North Portland at an ADU that we're building. This one is a zero energy ready ADU, getting this certified through Earth Advantage. And so this project, it's in 798 square feet, got some really interesting features that really drive the energy consumption of this building down, and also focusing on the envelope of some of the embodied carbon. So we've got some interesting stuff to talk about with, we're doing a concrete-free slab on grade, for instance. So this is south pointing this way, and we've got a nice gable pointing that direction. We've got no trees or anything off in the distance there, so we get some really good insolation. So we get a lot of good solar hitting this thing, and when we're all said and done, this little building should actually produce more energy than it consumes. So it's going to be a net positive energy ADU. So really excited to show you some of the features in this one. So ADUs are slightly different than building a new home in the sense that they max out at 800 square feet. So you can't really go any bigger than that. And there's certain lot coverage considerations that you have to take into account. So there's setbacks, there's the amount of permeable area that the site can take. Things like that you have to pay attention to. And sites are usually smaller too. So that means things like, soils that are, on site for excavation, lumber packages, trying to get materials and trucks and staging, all that kind of stuff can be rather difficult with ADUs. And they're also hooked up typically to the main house. And so all that infrastructure has to get into the main house, and oftentimes that affects the electrical panel and some of the loads in the house too. So a couple things that are slightly different than building a typical house, but more or less ADUs really are houses. They've got all the same things that a house has, they're just smaller in stature. All right, so the first thing we're going to talk about is the most obvious thing here. This is the blue WRB, or weather resistive barrier, that we're using on this particular project. So this product is a SIGA product. It's SA500, so it's a MyVest is the name of the product, and the SA stands for self-adhered. And so what it is it's a membrane that is vapor permeable, but doesn't allow bulk water to get into it. And it's got a sticky back, so this gets rolled out onto the wall, and then here we've got some nice cork, pressure pliers, because it's got to have that tactile pressing of the WRB in order to activate that sticky acrylic backing that's on there to keep it adhered. So this product is our air barrier, and it's also acting as our weather resistant barrier in this case. So it's got multiple functions. Since it's vapor permeable, it allows vapor to dry to the inside and to the outside. The vapor control layer is actually the plywood, which is behind here, and we specifically chose to use plywood on all of our projects just because it's more resilient than OSB. It's slightly more expensive, but I think if you're building you know, a multi-$100,000 project or someone's home, I think it's worth spending a little extra money to go with something that's a little more durable than just OSB. So the back side of that OSB is the vapor control layer, which is the least permeable part of our entire building assembly here. So that's the part that we want to pay attention to, making sure that we're keeping it warm and letting that vapor out so that we don't get condensation. So other things to point out here, the air barrier is going to be continuous on this whole building. So it's going to go through the outside of the building here with our WRB, and then on the top, if you can see this little flap here, there's two little spots where it's opened up. This is actually a 18-inch roll of the same product that we lapped over the top of the top plate, and it goes to the inside of the building and then comes around the outside of the building. And so we tuck this WRB underneath that and then stick it to it over there, and that's going to create a continuous air barrier from the outside up over the top plate into the interior of the building, where we will see how that continues through to the other side of the building. So that's how the air barrier is detailed up at the top. And then the assembly, this little vent line that we're seeing right here, it is a vented assembly. It's a foam-free vented roof assembly, and we'll get into that in more detail later, but this is where the air intake is on the lower side of the soffit here. So the air is coming in through here, and then it's traveling up over and underneath the roofing to a vent up on the ridge. So the rest of the air barrier is connected down through the bottom of the bottom plate, and that is connected to our vapor barrier on the inside, which actually travels under the mud sill and then gets wrapped up in here and then connected to our WRB here. So that creates the continuous air barrier right here. Okay, so we're going to talk here about how we detail the rough openings of the windows to make sure that any incidental water that gets in there is not allowed to sit in here and cause any damage and run out, and also how we're going to connect our air barrier to our windows. So starting off, when we do our framing, we take this bottom plate right here, sort of the bottom sill, the rough sill of the framing, and we cut this so that it's at 11 degrees. So you can see here that it's got an angle pointing to the outside of the building. And so any water that could land on here will just naturally run to the outside. So we just do that with the framing, and that itself is angled to the outside. Okay, so once we start applying our WRB, we actually run these sheets just right over the windows themselves. So the WRB is just kind of hanging out in space right here. And then what we do is we just cut that WRB 45 degrees into the corners right here, and then fold it into the rough opening. So it's taking care of the protection of our rough opening for most of the spots here, with the obvious exception of these corners that it creates where we cut that in. So we want to make sure that, you know, this is our air barrier, it's also our weather barrier, so we want to make sure that we're protecting these corners. And so what we do is we take some of our tape, in this case this is a Sega Wiglove tape, and this is compatible obviously with the Sega MyVest tape, and it's extremely sticky. It's fairly vapor closed, and it doesn't allow any water to get in. So John here, our site manager, is applying this tape. It's got like a split back on it, so he's able to, you know, take off the backing on one side and adhere it, and then, you know, fold it over, and then pull the backing off the other side, and then fold that back up over, therefore creating that really nice tight seal there in the corner. And that'll get pulled over this direction. And so what this does, when we install our windows, is we're going to connect our air barrier on the inside, which will connect to the backside of the Wiglove here, and any water that gets in here will be directed towards the outside. So it's extremely tenacious tape. This stuff chemically bonds with this WRB so that it becomes like a monolithic layer right there. So it's different than your typical bituminous tapes that don't actually bond monolithically. So what John's using right here is these things are pressure sensitive, so you do have to either roll them out or apply pressure to them to get that chemical, that acrylic bond, to really bond with that WRB. And so we got this great tool. It's just a piece of cork, keyed into just some wood to hold on to with like a felt on the outside. And this is the same tool that we use to go over our WRB to make sure that it is fully adhered right there. So this is an important step that you want to pay attention to when using these self-adhered membranes. All right, so we're going to talk about the rain screen that we're going to put on this wall. So obviously we've got our WRB to manage our air and our moisture. And what we want to do is create a gap between the back of the siding and the building right here. And that's going to do a number of things. That's going to allow any incident bulk water that gets behind the siding to be able to run out. It's also going to create an air pathway from the bottom to the top that's going to allow this convection of air. So any moisture that lands on that siding, there's a principle called solar vapor drive. So if the sun comes out on and hits some wet siding, it's going to cause that moisture to drive through that siding. And then when it hits this gap that we're going to create on the backside here, that convection of air is going to allow it to dry out. And so what that'll do is it'll keep the paint from bubbling. Oftentimes you see this on the north sides of homes, or on the south side rather, where the sun comes out and hits that, the solar vapor drive causes the water to go in, and since there's nowhere for that water to go, it gets trapped, and then as it dries out, it reverses back to the outside and causes that paint to bubble. So this is going to cause your paint to last longer. It's also going to stop hydrostatic pressure from driving water into the building. And so with a typical WRB, like a mechanically attached, it's got little staples all over the place in here, and any hole is a potential entry for water. But for water to get in, you need a couple things. You need not only a hole, but you need a driving force to be able to get that water into there. And so hydrostatic pressure is when you get water built up behind the siding, and that water buildup actually exerts a force that can drive water into the building. So if we're separating the back of the siding from the building itself, that water falls out, you don't get that buildup of water, and you lose that hydrostatic pressure, so you don't get that driving of water into the building. So the fact that we're using a self-adhered membrane, we have less penetrations and stuff like that, but then putting the rain screen on top of it is also allowing for that reduction of hydrostatic pressure. And so it's kind of a belt and suspenders approach for really not allowing any water to get into our building, while at the same time allowing that convection for air to get behind it to keep our paint lasting longer, our siding lasting longer. It also allows some of the moisture from the interior of the building to come out through diffusion of vapor and then get whisked away instead of getting built up back behind the siding. So the rain screen has a lot of really great attributes to it. So the way we do this is we just take some 5/8" plywood. This is a PT plywood. It doesn't really have to be PT. This is just something that's locally available here. And this will get attached to the studs. We have 24 on center spacing for our walls here, so they're just going to get screwed right into the studs and the walls, and then our siding is going to get installed across this, and that's what's going to cause that gap right here for that convection current to happen. And then at the bottom we're going to have a bug screen, which is actually a product called Core Event, which will allow air to get through but won't allow critters and things to get back behind the siding, because this does create a gap where you could get wasps and bugs and vermin and stuff like that to get back there and live. So we want to prevent that, and so we're going to have some Core Event down here with a screen at the bottom, and then again at the top, once this is all the way up here, we'll have some of that up top there too, where that air will be allowed to escape. And we're going to detail this rain screen at all of our penetrations. So this will happen where there is a entryway for air at the bottom condition, and also at the bottom of any windows, the top of any windows, and again at the top of the building. So there's never a spot where the air can't get in and escape and create those positive currents. And there was a project I was on a few years ago where I was actually up on the ladder on the second story of a building, and it was kind of a cloudy, sunny day, and all of a sudden the sun came out and hit the side of this building, and I felt air coming at me. And what was happening is there was 2 stories of air that had gotten warmed up just from the sun hitting it, and it felt like like someone was actually blowing at me. There was that much air convection happening, and once I felt that, it just became really visceral. It was like, wow, this really works. We're getting a lot of airflow and movement through here. So you can just feel it that this is working, and it's really creating that drying and allowing for any incidental moisture to drop out and not get driven into our building. So this is the core event product right here, and it's just simply like a corrugated plastic that you can see right here, similar to like a cardboard made out of plastic. And this allows air to come through and get into our rain screen. What it's got on the bottom here is like a felt kind of product right here, which keeps bugs and vermin from getting into that gap that's behind our siding, but still allows for air to get through. And so this gets installed at the bottom condition right here. The gang will install this thing first, and then the rain screen actually gets installed on top of this, which in this case, going with a thicker core event, when we have our lap siding here, allows us to actually create that flare for that first piece of siding right there. So it's kind of a little trick that we've learned. This is going to get held up a little bit off the bottom here because we want to leave space down here for air to get through, and then that air can get into here without allowing bugs into the space. Okay, here we've got a really good view of our air barrier, our continuous air barrier, as it goes up over the top plate and into the inside of the house. So if you look up here, you can see that we've got that 18-inch slice of my vest, that, you know, self-adhered membrane going over the top plate, and then the plywood gets stood up, and then our roof framing is happening on top of that. So you can see the spot above the blue stripe is our roof framing, and that's where the insulated, the insulation is going to go. Below that is our air barrier, and so when we install this next layer of my vest right here, it's going to positively lap over the lower layer, but then it's going to get tucked underneath that flap, and you can see how the back side of that membrane right there, it hasn't been peeled off yet. So that'll get peeled off, revealing that adhesive layer, and then that'll adhere to the WRB, therefore creating that continuous air barrier up and over into the building. Okay, so one thing the Birdsmouth team does as kind of a matter of habit, which I love to see as the owner of the company, is they're marking whenever they see like a little hole in the membrane. They just carry Sharpies with them, and they'll just make a little circle. So you're seeing little circles on the membranes all over the place here where there might be a little hole or something like that. Although this might be a little much, if you're going for passive house levels of air tightness, it really doesn't take long. We tend to have the gang have little pieces of tape like this cut into little bits in their bags, so just at the ready. And so oftentimes they'll be walking by and someone will have marked that there's a hole here, and so they can just simply take some of this tape and stick it over the hole and cover it up. So, not rocket science. You could argue how anal one needs to get with these types of things, but it's great to be able to just pay attention. It really doesn't take much time to make a circle, and when coming by, cover it up. All right, so we're going to talk about the foundation here, how this works, and how we're protecting it, and then from there we're going to talk about how that integrates into our air barrier and our WRB. So what I've got right here is an ICF foundation, so that stands for insulated concrete form, and it is 2.5 inches of EPS foam on both sides here, and on the inside we've got this plastic strut where we have clicked the rebar per the engineer specs into these little grooves right here, and so they click in really nicely. And so we'll pour our footing, or we'll get our footing set up, we'll set these things up and install the rebar, and then the concrete gets poured in here, and that's what creates our foundation. And that's exactly what's going on behind this corner right here that we're looking at. So what we don't want to do is have just this EPS foam be the exterior of our building for obvious aesthetic reasons, but also because we don't want it to get dented or kicked or animals or anything like that chewing on it. So what we've done is we've actually had some sheet metal made that we've done some stainless steel, and that just gets applied to the outside of the ICF, and so that's what we're seeing right here. So it gives it a really nice look and keeps animals and critters and plants and people from kicking and denting and all that stuff. And it's a non-reactive metal, so it doesn't rust or wick or have any other issues with it. So it's a really robust system. This is about an R4 per inch, so this 2.5, you get R10 on each side of this, so we're getting a complete R20 thermal break on the foundation. So we're really separating this building from its ambient environment. So these things work really good for that. One of the things we try to do at our company is try to do all foam free above grade. We have yet to find a really super great cost-effective solution. There are some out there to go foam free below grade, but this is just one of those compromises we make. So we are using some foam in this building, but this is the only place you're really going to see it here. So as we pivot over here, I wanted to show how we're continuing our air barrier from this WRB on the wall, then down into underneath the bottom plate and into the interior of our building. So what we've got here is our ICF. Before we put down our mud plate, which is just that pressure treated 2x6 on the bottom, we put a piece of this 6 mil green membrane right here. So this is just a polyethylene sheet that is a vapor barrier, so no vapor can get through here. And so that goes down right over the concrete. We just leave it flapping on both sides. Then when we frame our walls, we simply pull this up and just temporarily tag it into the plywood wall right here, and then install our kickout flashing right here. And then this self-adhered membrane, you can see it's just really sticky, even on a cold day like today, will get installed over the top of this. And this connection right here, where this gets sealed on here, is where our air barrier is connected, therefore creating a continuous air barrier from the exterior wall connecting to our vapor barrier under that plate and then into the interior of the building. So that's what's creating our continuous air barrier. This simply just gets wrapped around here, and then again, that's going to get that pressure treatment. We'll come back around and do that to make sure that we're adhering that acrylic to our building really well. And it's positively lapping our flashing here too, so any water that would get behind our siding can drain down, positively lap here, and then this is tilted to the exterior and just simply drain to the outside. At Birdsmouth, we're always trying to avoid embodied carbon along with the operational carbon of buildings. So the operational carbon is what the energy that's used for running your buildings, your lights, your HVAC system, plug loads, all that kind of stuff. The embodied carbon is the carbon that is, embodied into the materials. So when you're talking about things like bituminous membranes or asphalts or foams or things like that, there's a lot of energy that goes into the production of those materials. And so one of the things we want to avoid, if possible, is, or lessen anyways, is the use of concrete. So it turns out that concrete is responsible for 8% of all the greenhouse gas emissions on the planet, just that one material. And that's due to the fact that when they're producing concrete, they have to heat the limestone up to really high temperatures, and it takes a lot of energy, and they're using fossil fuels for that. And it also involves the use of sand, and there's river basins and lakes and deltas and stuff like this are starting to really take the impact of all that sand mining. So concrete is actually a material you want to use sparingly and pay attention to. So we've come up with a solution for our slabs where we actually avoid concrete. So this is a concrete-free slab that we're going to talk about here. So we also want to make sure that we have our continuous insulation with the slab. We want to make sure that we've got our vapor barrier over the top of it to keep any incidental moisture from the ground. The ground is always at 100% relative humidity, no matter where you are on planet Earth. And so we want to make sure we're breaking that, creating a capillary break, and allowing for our air barrier to happen so that we can install our flooring. So what we've got here is some gravel on the ground right here. This top layer right here is quarter minus gravel. So the little pieces in here are 1/4 inch or smaller. And underneath this, we've got some 3/4 inch clean gravel below this. And that 3/4 inch gravel is actually doing a number of things. It's creating a soil gas depressurization field. And so soil gases such as radon and stuff can then be, through a system of open tubes that we've got underneath here, sent to a pipe and then exited through the top of the building so that soil gas does not get into the building. The other thing that it is doing is it's actually a capillary break. So any moisture that's in the ground, we don't want to have to get into the building. And so we break that, that wicking that happens with the capillary effect. With the 3/4 inch gravel, there's enough gaps and spaces in between that gravel that water is unable to capillarily wick through there. So that's doing a number of things, including one of the things that we focus on a lot is the health component of the building. So it's keeping the soil gases and radon outside of the building. On top of that, we've got this quarter minus gravel right here, which is going to create just a place for us to screed this into a flat position, at which point we're going to set this foam on top of that, and this is going to create our thermal break. This particular foam that we're looking at here is a GPS insulation, so it stands for a graphite. It's an EPS with graphite in it. And so that's what gives it this kind of gray-black color. And by adding the graphite to it, it does a number of things. It actually makes it a little less permeable. It ups the R value from a typical EPS is 4 R per inch, and this is a R5 per inch right here. So this is a inch and or 2 inches of EPS, so this is R10. And we're gonna have 2 layers of this below our slab. So we're gonna have an R20 below our slab that's going to be continuous all the way across. And so this is actually going to end up going over here into the corner. Okay, so here I want to talk about a number of different things, including how this whole assembly comes together. So starting with our green polyethylene layer here, this is that 6 mil vapor control layer and air barrier that we saw when we were looking at the outside of the building. So this layer here goes on top of our ICF footing after the concrete's poured, and then we set our mud sill on top of that. And on the outside, that wraps up the outside and connects to our exterior WRB, continues underneath here to the interior. And so we want to continue our air barrier into the interior, and so this is the flap that's going to allow us to do that. So what we do is we temporarily take this up while we then set the gravel layer in here, and this will get screeded out so that it's perfectly flat. And then we're going to take our EPS insulation and set this down into here, and we're going to do 2 layers of this, and this is actually going to get staggered. So when we do this, ultimately it's going to be 4 by 8 sheets, and that'll get staggered so that we're not getting any gaps for air movement or anything like that to create a really nice R value down there. And so this will get set 2 layers deep here, and that's going to connect with our thermal boundary with the ICFs right here, therefore creating that continuous unbroken insulation up into the wall area. We always want to make sure that we've got a continuous thermal boundary along with that continuous air barrier. And then once we get this set, we're going to flap this back down here, and this will come down over the top. And then we're going to then roll another sheet of this out into the field and then tape it all together. So that's going to create our continuous air barrier from the outside under the plate to here, get taped throughout the whole building, and then the same on the other side. So we're creating that perfectly continuous air barrier there. This is also our vapor barrier. So this is also keeping any incidental vapor and moisture from getting into the building, because this is vapor impermeable here, and this gets completely taped. Any penetrations for plumbing, radon, stuff like that will also get detailed and taped around there to make sure that we're keeping that vapor in the ground and not into our building. So once we get that all detailed right here, what we do is we're going to install 2 layers of 3/4 inch plywood that are going to be staggered seams, which is going to create a floating subfloor essentially. And we're going to hold that back about 3/4 of an inch from the wall to allow that to expand and contract, because wood will move over time. And that'll simply get set here, staggered seams floating, and then we attach our finished flooring to the top of that. And so that way we're creating a really robust, airtight, vapor managed, fully thermally broken, concrete free foundation. Okay, here we're going to talk about our framing strategy, and what we went with here is kind of a hybrid. It's not a pure advanced framing because we do have a double top plate, but what we do have is our 2x6 studs are framed 24 inches on center, so you can, as opposed to a more traditional 16 inches on center. So that's doing a number of things. Every time you have a stud, it's a thermal bridge, right? So it's a conductive way for heat to get from the inside to the outside through this pathway right here. So when we're using 24 inches on center, a typical house with 16 inches on center is about 25% of the wall is just solid wood when you add up all of the studs. And if you go to 24 inches on center, it brings it down to about 17, 18%. So there's a lot of thermal bridging and therefore heat loss. All this energy that we're creating in our buildings can escape through that. So we're reducing that. And instead of having more wood, we're getting more insulation. So again, breaking that thermal bridge to the outside. We're going to be filling our walls here with a dense pack cellulose insulation. And so what we're going to do is we're going to have a membrane, just like it's like a mesh that's going to get stapled across this. And that's going to happen after all the trades come through. So after the electricians and plumbers and all that stuff come through, we're going to staple that mesh here and then blow cellulose into the wall cavities. And what that does is it allows that cellulose to get behind all the boxes and wires and doesn't leave any gaps or anything like that, so that we get these little voids where we're not getting that insulative value and create convection currents and stuff like that. So it's a really nice install so that we're getting a lot of insulation in here without any of those gaps or voids. Another nice thing about the cellulose is that it's got the ability to take on a bunch of moisture. So it's got this storage capacity of materials. It is hydrophilic, so it actually likes moisture. It'll take on that moisture if it's getting more, let's say there's showers or you're cooking pasta or there's a bunch of moisture happening inside of the building. It can take that on without falling out and creating condensation or liquid water. And then as things dry out, it can diffuse back to the outside and let that moisture go. So the cellulose is actually acting as a buffer to some of these vapor swings that you can get inside the house, which is really important to pay attention to when you're working with an airtight building. You want to make sure that you're managing any of those potential vapor swings. And so the cellulose is just one of the multitude of factors or items that we use to manage that. Okay, so when we fill this thing up with our cellulose, this is going to be 5.5 inches of cellulose, and we're going to test the density. We actually have a density tester to make sure that we're getting about 3.5 to 4 pounds of pressure per square foot, so that we know that we have a really tight install so that we prevent any settling from happening over time. So that's one thing we want to avoid. And when this is all the way full, it's going to get us an R23 is going to be the value of the R value that we're going to get in these walls. And since we're working in an ADU, this is a smaller building. They max out at 800 square feet. So there's a smaller surface area to volume. So we elect to not go with any exterior insulation on a smaller building like this because the amount of occupants and the internal heat gains, and along with the appliances, any computers you got going on, your TV, your lighting, is all going to add heat to the assembly. And so when we did our computer modeling, we found for these smaller buildings, such as the ADUs, it really doesn't make a lot of sense to use any more insulation to the exterior. So we actually went with just a simple 2x6 wall with that dense packed cellulose, and that R23 wall works really well for us to meet our zero energy targets in this particular building. Okay, here I want to point out how we deal with our headers with advanced framing. So what we've got here is our king stud that goes all the way up and carries the loads from the building on down to the foundation. And this is doubled up here because this is actually a shear wall. So this is something the structural engineer had called out. But in theory, this could just be a single king stud if this wasn't part of a shear wall. Nevertheless, what we want to do is avoid as much thermal bridging and framing as possible. So what we do is we actually use a hanger right here for our header. That's going to carry the loads from the rest of the building down and spread it across the window and down. And by hanging this here, it allows us to avoid an additional framing member called the jack stud that would normally have to come down right here. So we're able to remove some lumber, which actually saves not only on cost, but is less thermal bridging and allows us to get more insulation in there. And since we've hung this header right here, it allows us to also get more insulation in front of that header so that we break that thermal bridge right there too. So we're going to talk a little bit about some of the ways that we reduce the amount of waste that gets used and accumulated on a job site. So we will be ordering materials that will be the right size for their usage. So we're ordering 10-foot 2x6s here because we know that we've got just shy of a 10-foot wall ceiling break right here. So we're reducing the amount of offcuts and stuff like that that are being generated, and therefore reducing the amount of wood we need and reducing the amount of waste that's leaving the job site. When we do get offcuts and stuff like that, we always put them aside and they get used in the building. And one of the ways we do this is also part of an advanced framing technique where you've got our California corner. So at the corner of the building, oftentimes you'll see in a typical building, up to 4 or 5 studs in the corner. And so that doesn't allow you to get any insulation in there. It can be a really big thermal break. So what we do is we simply take, there's 2 studs here. We've got one stud in the back corner, and then we've got another one perpendicular to it right here. And then these pieces right here are just simply some of those offcuts that I was talking about before that get repurposed into the building. So in this case, they just get nailed into the corner here, and then that allows us to put our drywall in here and attach our drywall into each corner, and allows us to then get insulation back into this space. So we're using less lumber, reusing materials, allowing us to attach our finishes while getting extra insulation into these corners. So a quick tip here in terms of a really good thermal break, something that's just a quick thing you can do that's pretty impactful. This is where our bottom plate is right here. If you, our vapor barrier goes underneath the EPS forms right here, and normally you just have your 2x6 bottom plate right here. And so what we've done is we've just taken a little slice of 3/4 inch GPS foam and put this right here behind the baseboard. And what this is doing is it's breaking that thermal bridge of the bottom plate that would normally conduct the heat or the cool from the inside to the outside. So quick little, it doesn't take long. You cut these things, smack them in here before you put in your baseboards, and really makes a big impact, especially when this gets energy modeled. You can see how those heat flows really get stopped by doing this simple little trick. Okay, we're going to talk a little bit about some design considerations, especially in regards to window placement in our buildings. This particular building is an ADU, so in some ways we weren't able to really play with the orientation of the building to really take into account neighboring trees and solar, access and all that kind of stuff. Because with an ADU, it's in a backyard, and there's only so many places you can put it, so you're fairly rigid. So when it comes to design and placement for windows, we want to pay attention to not over glazing our windows if we can avoid it, because any window, even the best of windows, are going to be about an R7. Some windows will get up to R10, but when you're dealing with walls that are R23 or even higher, the weak point is the window. So you don't want to overglaze your windows. So that's one thing we paid attention to. The other thing is just sight lines and privacy, especially when it comes to neighbors and the homeowner's house right here too. So this back wall right here, we've got a neighbor behind us here to the west, and we've also got a neighbor to the south over there. So these 2 walls here generally have the least amount of windows because we want to pay attention to not staring into the neighbor's yard or vice versa. And then on the opposite walls that are facing more of the client's home, we've paid attention to things like adjacencies and sight lines to make sure that any windows that we have, we're not zeroing in to their living room or their bathroom or something like that. So paying attention to those privacy concerns there. So that was what was really driving the selection and location of windows in this particular project. Whenever possible, we try to put our windows on framing, so every 24 inches if possible, to set your window without having to do an additional stud there to reduce some of our framing material. We've tried to pay attention to that. In some circumstances, due to architecture and things like that, it's not always possible, but it's a really good thing to pay attention to avoid any of that extra thermal bridging or additional usage of wood if possible. Here we're going to talk about how we continue the air barrier at the top of the building, or at the top of our wall. So on the outside, we've got our WRB, and as you recall, we had put that 18-inch layer of WRB over the top of our top plate. And so what we're looking at here is our top plate condition. And this blue piece right here is that flap that we laid over the top right there. And what we've done is we've simply wrapped it over, adhered it to our bottom plate, and then taken our membrane right here, this is a Siga Myrex, and then connected it with the tapes to this membrane, and that continues our air barrier from the outside over the top plate to this interior membrane, which then travels across the building and connects to the other side. So that will connect our ceiling over the top plate, goes down the WRB, down the walls, and then goes through the bottom plate, under the bottom plate, to our vapor barrier on the foundation side. So that creates an unbroken, continuous air barrier all the way throughout the whole building. We're going to talk about how we're creating our roof assembly here. And so what we've got here is a foam-free yet vaulted and vented roof assembly. And what we're looking at the bottom here is this membrane right here, which is a SIGA product. It's called SIGA MyRex. And what this product is, it's a variable vapor permeability membrane. So as things get more moist inside the building, this membrane actually closes down its pores and prevents moisture from getting in here. But it's still permeable, so some moisture will. So it's controlling the amount of moisture that will get into our ceiling or assembly in the first place. And then we're using a cellulose insulation in here, which is hydrophilic, so it can take on some moisture as it needs to. And as things dry out here, as this membrane experiences a lower relative humidity here, so this could be in summertime, it could be different times of day, maybe after you've gotten out of the shower, the relative humidity in here will go down. And as this experiences that lower relative humidity, it actually opens up and allows some of that vapor that's in here, that moisture, to then dry to the interior. So it's really managing the amount of vapor that's getting in and allowing it to escape depending on the relative humidity conditions that are being experienced within the space here. So really cool high-tech product here. It's also has another function, two other functions. One is it is our air barrier. So this membrane is airtight. You can't get air through here. So this is our primary air barrier right here, which is why we have it taped at the seams. So again, that's getting taped at the edges that go over the top plate, continuing up, tape all the seams, and that creates our air barrier throughout the whole thing. The last thing that it's doing is it's creating a spot for us to blow in our insulation. So this is also being used as our insulation netting. So when the insulators come, they're going to cut holes into this thing, and then they're going to put their hoses in here and dense pack this full of cellulose insulation. And then when they're done, they'll pull that back, and we'll take some of this green SIGA Reson tape and then cover that up, therefore creating that continuous air barrier. So it's actually physically holding that insulation in there. Now, on the top side of these 2x12 rafters right here, so we've got 12 inches of insulation at about R4 per inch, so it's roughly an R48, R50 roof assembly right here. On the top side of that rafter, as it's coming down, we've actually got another membrane on the top where we've actually just used a Tyvek. It's a commercial grade Tyvek on top. So it's very vapor open. And on top of that, we've got a 2x4 strapping, then our plywood, and then our roofing. And that's creating an 1.5 inch vent chamber. So it's allowing the roof to vent from the eave over the top of that Tyvek, over our roof assembly, and then out at the ridge. So we have a vented assembly. Since that top layer is so vapor open, any vapor that gets into this cellulose assembly can diffuse through that membrane and then get whisked away from that vent chamber right there. So we've actually got a vented assembly that's vaulted, that is really durable, that won't experience any vapor problems, especially in a colder climate. This will work really well for any climate that you're building in, without the use of petrochemical or plastic foams that can be problematic for a number of different reasons, whether that's recyclability or the amount of embodied carbon, the health of the workers that are using this foam, the repurposing of the building, end of life cycle constraints, air tightness constraints. All these things kind of can be problematic when using plastic foam. So we've managed to completely avoid that here while creating a really high performing and vapor managed vaulted assembly. So the last thing to point out here is the strapping that we've got going across here. This is doing a couple of things. It is actually just holding this membrane in here, so as this gets dense packed with cellulose, it just doesn't peel off the wall because it's just being held on by these staples here. So it is holding that cellulose in there. The other thing that it's doing is creating a service chase that we can then run our electrical wires and stuff like that in here, and then do a shallow electrical box in here with like a pancake style LED light, and that allows us to get lighting in here and electrical without penetrating our air barrier or our thermal boundary right here. So really high performing, versatile, durable, vaulted, foam-free roof assembly here. So here we are in our tiny little space where we've got our heating, cooling, and ventilation system. This is called a Minotaur. It does the ventilation and the heating and cooling all in one. And so as part of this, it is a ducted system. And as you can see behind me here, we have designed it so that all of our ducts here are within the conditioned space. And we've got a little gap from, you know, the upstairs unit to the downstairs that's about 7 inches tall, where we've been able to get some ductwork through. And that was designed in from the very inception of the project so that we could, you know, deliberately keep all of our ducts within the conditioned envelope right here. The ducts themselves are all taped and sealed so that we don't have any duct leakage, so that we're delivering the proper amount of ventilation, heating, and cooling to all the different spots of the home. So really important to design this in to your projects as early as possible, and bring in those trade partners. If that's your HVAC partner, you know, bring them in early on in that design so that you don't end up having a real difficult time, especially in a small, you know, ADU where you don't have a lot of space. You really need to think of these things early on. Okay, so I want to touch on what this particular unit is doing. It's a 2-in-1 unit. It's bringing the fresh air, so the ventilation, in from the building. So there's a supply that's running from the sidewall, and then there's an exhaust that goes up through the roof. And so this unit is providing fresh air. It's actually taking the entire volume of air in the house and replacing it once every 3 hours roughly. So you're always getting fresh air in the house. You don't get CO2 spikes, and you have plenty of oxygen in the house. And it's also dealing with the humidity in the air. And so this unit can ventilate, it can heat and cool, and it also, you can set the humidity where you want it to be within the house, so it can control the humidity all in one unit. And it's got a condensate pump down here, or drain line rather, so any water that gets pulled out of the air will come down through this condensate line and then go to a drain that we've got downstairs. So this unit is an HRV, so it's taking a day like today where it's really cold outside and it's warm in here. We've got it set to about 68 degrees interior temperature here. So it's taking the cold air from the outside and it brings it in, and it takes the warm air from the inside and passes it along that incoming cold air, but it doesn't mix with it. It just passes along, and it transfers its heat from the exiting warm air into that incoming cold air so that it's tempered by the time it gets in here. And this particular machine gets a heat recovery efficiency of 101%, which seems insane, but because it's also providing the heat, when it's in heat pump mode, there is some residual heat left in those coils that incoming air can use. So it transfers not only all of the energy from, it doesn't quite transfer all the energy from the exiting air, but it gets about 90, probably 3% of it, but that additional 7-8% is got from the heating component of it. So it actually delivers a more than 100% heat recovery from the outdoor air to the indoor air. So that way we're able to provide fresh air to the occupants directly from the outside that's tempered, so we're not losing any of the energy that we've created inside the building. Now, while that's happening, this runs through a set of filters. It's got a MERV 15 filter right here, and it's got 2 pre-filters. And so this filter right here is going to take out any particulates, particulates that are smaller than smoke dust. It gets rid of particulates that are the size of viruses and bacteria. It gets rid of, any pollens, things like that from the outside, or any allergens. So not only are you getting fresh air exchanged once every 3 hours, but it's being run through a really tight filter that's removing this. So you're delivering super fresh, high quality air at all times to the occupants on the inside. So these filters do get pulled out and they get exchanged, every I think it's every once a year for the bigger filter, and then once every 4 months for these pre-filters right here. So this unit, at the same time it's doing all that fresh air filtering and ventilation, is also providing our heat and our cooling. So it's essentially got a manifold that'll direct the air either to the heat pump mode, so it can take the ambient heat from the outdoor air that's brought in through our supply and take, even on a cold day, there is still heat in the air, run it through a heat pump and then concentrate that and then send that into our supply on the inside of this environment right here. And so it's doing that with a SEER of about 14.1. So that's a really high, or rather the HPSF of 14.1 on this. So it's got a really high efficiency to deliver heat in here. And then that heat pump can be reversed, right? So it can take the heat from the inside and dump it to the outside. So that's air conditioning in the summertime. So this can cool the house in the summer and heat the house in the winter, while doing it at a really high efficiency. The other thing that this unit is doing is that it can actually sense the humidity. It's got a humidity sensor in here. So let's say, for instance, you're taking a shower and it gets really moist and humid in that bathroom. It'll be exhausting that air from the bathroom and it'll sense that it's a really high relative humidity. So it'll direct that humidity to the outside and reduce that humidity inside the house. Or alternatively, if say it's wintertime and we're running at a really low relative humidity inside of the house, it'll take some of the moisture from the outside and bring that in. So you can avoid like the wintertime chapped lips and dry skin, dry nose, nosebleeds, that kind of stuff by keeping that relative humidity in here. And it's constantly sensing where it's at. And you can actually set that at the controller so that we're really conditioning the air to be at that really nice, between 40 and 60% relative humidity, allowing for heating and cooling, allowing for fresh filtered air. And it's also balancing the pressure between the outside and the inside. So this thing is taking out as much air at the exact same rate as it's delivering air. And so what that does, if you think about your airtight envelope, there's no pressure differential. There's not like you're creating a pressurized inside by doing supply-only ventilation, which is then causing all your air that contains moisture and nasty stuff to get forced into your wall assemblies and then potentially deposit moisture or cause mold or harm or rot or something like that. If it's the same pressure between the inside and the outside, there's no way that the air is going to be directed through exfiltration or infiltration into your building assembly. So this is also making this building last longer by keeping all of that moisture from getting into our wall assemblies in the first place. So this thing is doing a lot of work right here. It's also really compact, works really well for the ADUs and also any other house. You can get this with a post heater on it if you want to have a little more horsepower. If you were trying to heat a 3,000 square foot home with this, it probably wouldn't be enough. You might have to use 2 of them or use some sort of post heater on it. But for these really super low load, high performance homes, especially in a smaller setting like an ADU, this is more than enough. Again, it's about 37 degrees outside today and it's perfectly comfortable inside of here. So here we're talking about our water heater strategy, and since we're in an ADU, we wanted to find something that was compact because we don't have a ton of space in these 800 square foot buildings. And so we also wanted to find something that was highly energy efficient. And on top of that, we wanted to make sure that we were delivering enough hot water for the occupants without running out of hot water. So we ended up using the Sandin water heater. It's an air to water heat pump. So what we're looking at here is only half of the hot water heater. What this is just a stainless steel tank. There's nothing else in there. And then we've got some plumbing penetrations that go through the exterior wall. And on the outside, we've got the compressor and condenser unit, which looks a lot like the outdoor unit of a mini split. And it's got a fan. and it's charged with CO2, so it's not using a refrigerant like one of the R1 refrigerants that are really bad for the ozone layer and the environment. It's a really nasty greenhouse gas, whereas here we're just using CO2 that's under high compression. And so all we do is we run a hot water line and a cold water line from this tank to the outdoor unit, and that outdoor unit takes the ambient heat from the air outside and compresses it and delivers that into those plumbing pipes, and then delivers that hot water into this tank. And so it does it at a really high efficiency. So the rated efficiency of this on average is an energy factor of 2.65. So that means that it's getting 265% efficiency when compared to combustion. So the best gas-powered hot water heater you could get will only get about 97% efficiency, where this will get 265 on average. When it's a warm day outside and this thing's functioning at its best possible, it will get up to 500% efficiency. So 500% the efficiency of what you'd get from an on-demand gas or any type of gas unit. Now, the nice thing about this is that because it's not a combo unit, which is really common, it's a great unit, is they'll have the heat pump compressor on top of the tank, but it's gathering the ambient air from the inside of your building, and so it'll tend to dump a lot of cold air into the building, and so that can, you know, go against your heating system, and they'll compete. This particular one, since that is separated and we have that condenser outside, it doesn't dump any cold air into our space here, so we're able to be really warm and cozy in here and get that great efficiency. The Sandon actually holds the water temperature a little hotter than a typical hot water heater, so it's going to hold the water about 145 degrees. And so that means that we actually have to mix in some cold water from the exiting tank before it gets delivered to the fixture, otherwise it would be too hot. This has the net effect of this 40-gallon tank actually behaving like a much larger tank. So that way we can have a small unit with really hot water. We mix cold water to it to deliver to your shower, but that way it acts like it's a much bigger tank and we're not going to run out of hot water, because we want to pay attention to that. That's that whole comfort thing for our clients. So really great and impressive unit. In this particular location, since we're in an ADU, we're really tight for space with 800 square feet. So we designed it from the very inception so that it can fit under our stairwell right here. And where I'm standing right here, or crouching down rather, is where we're going to have the fridge, and the fridge will be flush to this here, and that'll cover the water heater back there. So you won't even realize where the water heater is. We do have a drain in back, and there is going to be a pan that this will sit in when it's finally installed, so that if this thing does overflow or there's an issue, it will drain into that pan and out the drain, so we're not going to flood the rest of the house, and keep that safe too. So really like these units, really special units, and they work great for these ADUs or for any really high performance home. All right, so let's talk windows. So here in this ADU, we've decided to go with a triple pane unit. It's a fiberglass unit from Alpen. And these are super high performance windows with multiple air seals. They've got not triple pane glass in this particular one, but with the Alpens, they actually have a suspended film that makes that third pane on the interior of this glass right here. So it goes right in the middle, and then that's filled with an argon gas inside of those panes, which is less thermally transmittive. So it lets less of the heat out or cold in, depending on how you want to look at it. So this is a casement window, so you crank it and it cranks out and then seals back in. These are one of the more efficient styles of windows. So something like a double hung window or a slider is less efficient because it's not as airtight. It's because you've only got that one gasket that's sliding back and forth, whereas this actually like shuts in on itself, and you got multiple gaskets that can get compressed. And then when you close this down, it actually locks it into itself and compresses those gaskets so that we're getting a really airtight window. And that's one of the more important things from a window. You could have a great, U value of your window that's really thermally broken. But if it's leaky, you get this thermal bypass that happens, and all the energy you're trying to save is just going through the leakiness of the window. So one thing people don't pay attention to often enough, in my opinion, is how leaky is the window, and what is that rated as. So this is rated as a really, you know, airtight window. And one of the things about this too, with all of the moisture and vapor that's happening in here, let's say we're cooking pasta, we got house plants, we just took a shower, we're creating all this vapor. On a cold day like today, it's about maybe 37 degrees outside, and tonight it'll probably get down below freezing. What we don't want to have happen is that, you know, moisture condensing on a beer can kind of thing, where the warm, moist air in here hits a cold window and condenses. I'm putting my hand up here right now, and I really can't feel much cold coming off that window right now because it's thermally broken because of those triple panes. And so you want to avoid that for obvious reasons. We don't want to have water be hitting here, dripping down and creating potential for mold growth or bacterial growth, that kind of stuff. So another great thing about these windows is they have these warm edge spacers in here. So these are thermally broken spacers that hold the panes apart from one another so that you're not getting thermal conductivity through those spacers. The other thing that these have is the frames themselves are also insulated, so there is an insulation in the frames so that those are thermally broken too. When we install these, we actually bring that WRB into our rough opening, and then we take a tape called a Siga Fentrim tape, and we tape that on the interior of the window all the way around all four sides of this window so that our air barrier comes through, hits the window, and is sealed from the inside here so that we don't let any air through our rough opening in the window. Then we install it so that both sides and the top are positively lapped on the outside to keep water from getting out, but any incidental water that will get in your window, and all windows eventually will let some water in, is allowed. We don't put any sealing, we don't seal the bottom sill of the window on the exterior so that any water that's in there is allowed to drain to the outside too. Therefore, creating a really durable and resilient assembly, something that's thermally broken, lets good light through, and is airtight. So we try to avoid, just like we're avoiding plastic foams above grade, we try to avoid plastic in our windows. So this is a fiberglass unit as opposed to a PVC or a UPVC unit. We avoid plastics for a number of reasons. One is that they're not as structurally sound, and especially when UV light hits them from outside, it can cause the windows to sag or deform. It's one of the reasons why you'll see separation of the panes from the frame itself, is because that plastic PVC will get affected by UV light, and over time that can, you know, break the seal on the window. And the other reason we do it is that we're also paying attention from like cradle to grave. So someone is producing these windows, and there is some worker somewhere that's working with these, you know, plasticized polymers that is affecting the health of that worker that's creating these things. And, you know, fiberglass also just has less embodied carbon than the plastics do. And with plastic pollution, microplastics, off-gassing, all these things, we just avoid using that PVC in our projects. That said, there are some windows that are made out of something called a UPVC. These are found in Europe. They don't have some of the component of the plastic that keeps it from being flexible like you'd see in the United States. And those are more durable. So oftentimes you'll see European windows that have that UPVC, and those are a better product in terms of their durability, but they still have some of the downsides of the issues with plastic. So we tend to go for a fiberglass or a wood or an aluminum, things that are natural materials that can be repurposed later, can be recycled, or have a lower embodied carbon in the first place. So we test all of our homes when we get them dried out. So as soon as we've got our air barrier complete and we've got our windows and doors installed, but prior to having the insulation and cover put in, so this would be after the plumbers have come through and the electricians and all this kind of stuff, we test with a blower door, and that's to see if we've got any leaks. And we do it at that point prior to cover so that we still have an opportunity to get in there and track down any holes or anything that cracks, things we might have missed, so that we can seal that prior to putting in the insulation and the cover, because once that's up, then it's just too late and you can't really track those things down. And then we always test the blower door once all the cover is done, and so that we can get a final blower door test and see if anything has happened from that stage. If some plumber came along without us knowing and put another hole in the wall, we test at the end of our project so that we could find any of those mistakes too. So when we did a blower door test on this particular home, we ended up with a blower door score of 0.4 ACH50. So that's 0.4 air changes per hour at 50 pascals pressure. So for a point of reference, Passive House is looking for their international standard at 0.6 ACH50. So this particular little unit is doing better than Passive House in terms of its air tightness. So we did hook up a blower door to this location here, depressurized the house and pressurized it so that we could see how that changes between pressurizing, blowing up the house, and then sucking the air out of the house. So that we can make sure that we're not getting any leaks. Again, those leaks are super important because air contains moisture. Moisture can get deposited into your wall assemblies and can wreak havoc with them. So really, amongst other good reasons, including air quality, particulates getting in, all sorts of stuff, that's the way we can really test to see how quality of our air barrier is and how quality, by extension, our building is. Okay, we want to talk about how we're protecting the site. Any construction site that you're working in, you got large machines, you got excavators, you got people walking back and forth, you're disturbing the soils, and you really want to make sure that you're protecting the site itself. And so we want to make sure that we're getting all this erosion control material in place prior to starting any project, and then making sure that we're maintaining it throughout the project too. And so you can see here that, we've got a slope here, and so we've got some retainage happening here to keep the, as the machines roll up here and people are coming and going, keeping all of the soil in place and not allowing it to slough down into the sidewalk. And then we've also got these straw wattles, which are also keeping any muddy water or anything like that runoff getting filtered through that before it gets into the sidewalk and into the street. And the reason that's important is that, native fish like salmon are really affected by water siltification and turbidity and stuff like that. So as you take the aggregate of all the construction and things that are happening in a city, and you think about that rainwater, stormwater getting run off into the street, into the storm drains, and then into the rivers, it really siltifies the water and can really affect wildlife. And so what we're trying to do here is just keep all of the mud and silt and all that stuff in place, managing it on our site so that we don't get that running into our sewer drains and then eventually off into the river. Okay, so we're going to talk a little bit about some of the stormwater management that we have here. So all the water and rain that hits this building right here, we want to make sure that we're not sending it into the combined sewer system and off into the street. But the reason being is when we get large rainstorms here in Portland, Oregon, sometimes when you get all of that water that's hitting the buildings and that goes into our sewer system, it can overwhelm the system, and then sewage and stuff like that can get into the Willamette River, and we want to avoid that. So what we do is we manage all the stormwater here on site. So what we're looking at right here is just a simple downspout for the gutters. It'll go from the gutter back down to the downspout and collect into here. But this pipe is actually running to some dry wells that we've buried underground here that basically are a concrete ring that's filled full of gravel, and all the water gets hooked into that, and that slowly allows all that water to percolate into the soils and then just go down into the groundwater. So that way we're managing all the stormwater here on site and not sending it out into the street and adding to that potential of overwhelming the sewer systems and really affecting the rivers and the waterways around town. So why is Birdsmouth building beyond code, and why do I think that other builders can easily move into this? The reason we're doing this is because we're, it's like a win-win-win situation, right? So you're saving energy by not combusting gas and using heat pumps and, saving energy through the envelope. And that's great, right? Because we need to save energy. We need to stop putting greenhouse gas emissions into the environment, all this stuff, avoid fracking and pipelines through native lands, all this kind of stuff. But the beauty of it is that you're actually getting a better product on top of it, right? So, I certainly, as Birdsmouth, we have our value set where we want to affect climate change through the built environment, but we also are craftsmen and designers and architects that want to build something that's better for our clients. And so by using a heat pump, heating and cooling system, building all electric, using a, heat pump, air to water, hot water heater, actually delivers a better product. These homes are more comfortable. The walls are 70 degrees, the floor is 70 degrees, the air temperature is 70 degrees. So you're not getting any of these like cooling feelings from your body losing its heat to the windows. And so you're getting just a better experience of the house. You're also getting much higher indoor air quality, right? So things like wildfire smoke, viruses, particulate matter is getting filtered out into these buildings, and they're not allowed to get into the building in the first place because of our continuous air barrier. So you're providing a space for our clients that not only saves energy, but is much more healthy, right? So that this is what people want in their houses, right? They want to be comfortable, they want to be healthy, and they want to be secure. I mean, these are the emotional reasons why people want to have a quality house. And zero energy building not only hits our values for that, but it's also what people want. And so we're able to bring these two things together in a way that is creative. There's a lot of problem solving. It's cutting edge. So there's new technologies. We're learning a lot. We're educating our staff. We're educating others. So it really fulfills our mission and provides something that's just a better product. You can use an induction range and it can cook as well or better than gas. You can have a heat pump hot water heater that's delivering hotter water than a typical hot water heater and is a smaller size, and you can deliver that inside your house. It's better. We're not combusting things and having nitrous dioxide, carbon monoxide, particulates brought into the space. So your lungs, it's cleaner for the people living there. So all of these things come together to create a really great scenario where we can deliver not only just really high quality buildings, but buildings that are addressing such a big, impactful part of climate change in our environment, all at the same time while being creative, fun, and interesting. So we really enjoy kind of bringing this all together. And, I really do think that there are certain components of this stuff that once you learn how to do this and you build it into the muscle memory of your staff, your builders, your architects, it's not any more difficult than what you were doing before. I mean, anything we do has been trained. You've put on Tyvek, that's what you've always done. It's easy. Now we're putting on a self-adhered membrane. Is it actually any more difficult? No, in fact, I'd argue it's maybe easier, but it's different. And so there's definitely a learning curve and there's some resistance to that. But I think there's a lot of things that other builders can do and incorporate into their practice, especially over time, that can get you building to this zero energy, zero carbon target without really having to do anything much more difficult. Our staff often talks about it's just building. We're building homes that are reaching regularly levels of airtightness that are less than passive house levels of airtightness. And it's not like they're working any harder, it's just building. And it did take a little bit to learn these things, and that's hopefully why through this course we can teach you some of these things. I can take some of these things that we have learned and some of our mistakes, pass them along to you so that you can incorporate this into your practice. And I really do think that most builders can reach these levels of performance without having to really break the bank or completely retrain things. I think it's just a different way of doing things, and once you get used to that, it all comes together. At Birdsmouth, we've taken the time to really create a process all the way from when a client first contacts us through design and through construction that is a flow chart that we've created a system of kind of check sheets that go through each particular aspect of design and construction. And so that might be something as simple as, did we remember to get the questionnaire out to the client when we're in the programming stage of design? Or it could be something like, check this box now at this stage so that we know to bring the construction team into the office and work with the architecture team to be able to have that iterative process between the constructability aspects and what the team in the field really knows about construction materials and putting it together, and incorporating that cost effectively into the architect's design. And so we've got all these processes and charts and checklists that we've set up so that we really don't miss any of these things, so it doesn't kind of fall through our fingers. And so when you're thinking about doing a high performance design and then executing it in the field, the design build component is really important, so you can have that cost feedback, that constructability feedback, the efficiency feedback at the same time that the architects are doing that design, so you can work iteratively and as a team towards that same goal. So I highly encourage others that are considering this to really take the time to create check sheets, create a flow chart so that it becomes kind of a mechanical thing, so that when you move to the next phase of design or construction, that you're making sure you're checking off all these boxes and not missing any of these really important components. So over the years, we've definitely learned some things that we've incorporated into our practice and some other things that we've learned to stay away from. And so in our experience, we've really moved away from certain things. So what we found is that we've moved away from using things like recirc hoods in the kitchen. We like to, properly vent any of that, cooking particulates and all the gases that come from that out of the building, as opposed to using a recirc hood. And that's something that the Passive House gang was really into for a while, and we've kind of learned that it's better to get this stuff out of the building and take that penalty from having that hole in your envelope and some of the heat losses that come with it. So that's something we've learned. We've also learned to move away from using foam, petrochemical foam plastics above grade on our building. So things like closed cell spray foam, XPS foam, EPS foam. We've simply found that there's a better way to do it. We really think that if you're using foam above grade, it was a failure of your design team. Because if you design things correctly in the first place, there's really no need to be using that. So that's something that we've learned over the years. Other things we've learned, we've moved to a self-adhered or liquid applied WRB, so that's your weather resistant barrier. We found that these just perform better. They work really well for our air barrier. You don't have a lot of staples in this material. So we've just moved away from that over the years and found that we're getting better performance for that. Other little things would be things like plumbing recirc pumps or something like that. We can avoid that energy penalty of having a recirc pump that's, getting hot water pumped over to your faucet or your fixture so that when you turn it on, you get hot water right away. Instead, we found that through good design, if you locate your water heater and your plumbing runs so that there's home runs directly to these things in the shortest amount of time, you can actually get hot water to the furthest fixture very quickly without having to use one of these pumps that uses extra electricity. So some of this is a little bit in the weeds, but over the years, these are things that we have learned and just employed into our practice. So some of the reasons why clients are interested in green homes and looking to purchase a green home, I think it really boils down to what anybody really wants, right? We're emotional creatures. We want things that make us happy. And so really that's just being comfortable. It's being having a healthy place to live. It's being secure, right? So a green home, besides saving energy, and that is another reason why someone might want to buy a green home, is that it's going to save them energy and save them money. And it might reflect their values too, right? They want to do their part to put their shoulder to the wheel to help against climate change, right? So that's one way that they could do that. But all that aside, people really just want to be comfortable. If your walls are 70 degrees and your body is, warm, you're not going to lose your body heat to that wall as if you're standing next to a cold window. The windows are thermally broken. They're oftentimes triple paned. We're not getting that cold window. There's no drafts that are happening in the house, right? Because it's airtight. We're getting less stack effect. We don't have a lot of really loud and fast moving air that you would get from a typical gas furnace or something like that. So these homes are just generally more comfortable. They're also healthier, which I think is really playing into people's kind of thoughts when they're thinking about homes these days and where they're living. The average American spends 92% of their time indoors. And so we're slowly learning that there are so many conditions that happen to us health-wise that are related to our homes. If we're living in a place that has, formaldehyde or is off-gassing or has really poor indoor air quality because you've been cooking and releasing different gases and particulates into it. There's bacteria and viruses. All these things can be mitigated when you're just not using, when you're building a home, not putting these things into your house in the first place, and then filtering the air, exchanging the air, and it just makes for a much better experience of your health and your life when you're living in your home. And then finally, people want to be secure inside their homes, right? So a home that's built like this is going to be resilient. If it's the middle of winter and the power goes out, a really well-built and thermally isolated building will retain its temperature. Great examples of some passive houses in really cold climates where the temperature outside has gone down to -20, the power went out, and after a week, their homes are still around 65 degrees on the inside because that house really retains that heat, doesn't allow it to escape, and is oriented in such a way that we get those heat gains from the sun. So, there's a real sense of security that you can be in a warm, safe, secure home without having to, spend all this energy on it. And there's so many great things that come from that. So I think those are the main reasons why people would, and really should, want a green home, not just due to the energy savings, but due to all those really important emotional reasons why people want to own any home. So speaking about energy savings, this particular house has an EPS score. So this is your energy performance score that you get from the Energy Trust of Oregon of 30. And so that translates to about $45 a month for your typical energy bill for the entire home. Now this is a zero energy ready home, so it is pre-wired and we've got conduit going up to the roof here so that they can install solar panels. And once those are installed, that'll easily offset that $45 down to zero, or actually less than zero. So you could actually be positive as far as that goes. And so that energy usage covers all the heating and cooling, which is generally the biggest energy usage in the house. It covers all the plug loads, all of the lighting, so we're using 100% LED lighting in here, and it covers all the cooking and appliances. Anything that powers this house is all covered for that $45 a month. So really hard to beat when it comes to the economic savings and the energy savings in the house.